Fahad Khan. He's from the Mohammed bin Zayed University of Artificial Intelligence at Abu Dhabi, and he's also a visiting professor at Linkoping University. He has worked directly in some of the state-of-the-art video LLMs, such as Video Chat GPT, and task-specific LLMs, such as Pixel Grounding Video Lava. He's previously he's very interested in challenge participation. He's served as a member of the program committee for most conferences in the vision and ML space. And he's also been a guest editor for TPAMI. And he has frequently organized workshops at CVPR, ICCV, NeurIPS, and so on. He's going to present his talk on uh, detailed video understanding in the era of generative AI. Please. Oh. Yeah.
Thank you very much for the introduction. Yeah, so I'm going to present some of our recent results today on video understanding through leveraging large multimodal models. Before we start looking into video LLMs, so this is how the journey actually begins, or how I started exploring video understanding problems 16 years ago. And at that time, basically, we were looking into some basic fundamental problems, for instance, human action recognition. And the idea was, given an unseen video, we identify the correct action category that the human is performing. So these were some of the benchmark data sets at that time. KTH action was quite popular for benchmarking videos for this problem. And the ultimate goal at that time was to eventually be able to obtain a more detailed semantic understanding of the video content. So for instance, being able to completely comprehend the description of the video, or rather than just restricted on predicting category labels or classification labels, so to say. And so far, we have seen in today's talks as well, we are kind of observing some of those capabilities by leveraging large language models. So for instance, this is one example, a case here. So video chat GPT, and we can see from this example that the model is somewhat able to hold human-like conversations and also identify the activities that has been happening in the video a bit more accurately. However, there are still limitations, and it's still a long way to go. And there are problems, for instance, hallucination or processing long videos, and also grounding, which I'm going to cover today. So to this end, I will present some of our recent results on three distinct research directions within video large multimodal models. The first research direction is how we can develop semantically enriched video LLMs for detailed video understanding. The second research theme looks into making video LLMs more inclusive with respect to cultures and also with respect to linguistic capabilities. And lastly, we will also discuss some recent efforts on how we can make these video LLMs more efficient in terms of operating them in resource-constrained settings. So moving on to the first part of the talk. So we have seen in today as well, and if you're working with video LLMs, and they are, as I said, they are somewhat able to hold human-like conversations, and they can comprehend the video content as well. So for example, in this case here, I'm showing some example frames, and if I ask one representative model, Video Chat GPT, a question regarding, can you identify any safety hazard in this video? The model is able to somewhat give a more accurate response about the safety hazards. For instance, the child is too close to the fireplace, and this can cause some safety concerns or injuries or burns as well. So it is kind of comprehending the sequence of activities that is happening in this video. However, still, it is not able to really ground the different concepts or the actions that have been happening in the video with respect to the textual response. And this leads to this first limitation, which I'm going to discuss within video large multimodal models, that most of them provide a holistic understanding of the video content, and they generate ungrounded textual responses, and which leads to their struggle with respect to fine-grained spatiotemporal pixel level object grounding. So for instance, how we can intertwine the output, resulting textual output with the object mask or segmentation. And also, if we want to do spatiotemporal fine-grained pointing and again, object grounding, how they still struggle to achieve this level of detailed understanding of concepts. And both of these are actually important. So for instance, in case of interactive embodied agents or smart city applications, we tend to look into having a more detailed understanding of the video content in order to make some informed decisions. So let's look into the first research problem of developing video LMMs with the spatiotemporal pixel grounding capabilities. So we recently proposed pixel grounding video LMM named Video Glam, which will be presented on Saturday in the main conference. So it is designed for spatial temporal grounding in videos based on the user provided text. So for instance, if I am providing this input video, and I asked the question, can you provide a detailed video description with interleaved segmentation mask for each part? The output is somewhat like this from Video Glam, that the generated masks are spatially temporally consistent across the frames. And we can see, for instance, different level of granularities as well. So for instance, person, object, which is bike here, and also stuff, which is road here. So the model is able to ground these different concepts or different level of granularities with respect to the textual description. So there is a synchronization with respect to both spatial and temporal elements within the video, along with the textual instructions that is required to obtain this kind of a response. Sorry, it's still to stop. It's freezing. Please share the screen again. Okay, so yeah, so sorry for the glitch, but this is also something related to what Afshin mentioned in the video streaming talk, how these models still, I mean, if we want to do this in a live video stream, there's still some way to go. Okay, so yeah, I skipped the video part. So this is how we want to do this grounded conversation generation task that aims to provide video level detailed captions with specific phrases that are directly intertwined with the segmentation masks in this frame. So we can see on the left side the input video frames, and on the right side the output of the video glam, and how it kind of provides the detailed textual responses with respect to the segmentation masks. Okay, now in order to do this kind of a training or model training, we require a specialized fine-grained spatial temporal grounding data set. So we curate such a multimodal data set that features detailed visual grounding conversations in a semi-automatic pipeline, resulting into 38K video question answer triplets with 83K around objects and around 670K spatiotemporal mask. And with this kind of a data, then we trained this video glam model for grounded conversation generation. So how we do this in a semi-automatic pipeline? So we leverage existing data sets and we identify three different sources of existing data. So the first one is those data sources or data sets where only videos have masks representations. And to generate the corresponding dense grounded captions, what we do then is that we have object patches which are extracted from the video frames using the mask, and then we process them using a proprietary model, Gemini Pro model, for initial descriptions, which are then further refined to produce more detailed masks. And then the captions are generated, which we are further detailed, and we accurate them with two video elements, video lava and video lava next. The second type of video data set that we have used is actually having videos with only bounding box annotations and captions. So here what we do is that frames are first pre-processed with any video LMM to generate a comprehensive caption, which is then combined with the original caption and feed into GPT-4o in order to obtain dense grounded captions. And then subsequently for the masks, we generate these masks using frame and ground truth bounding boxes using the segment anything model. And the third type of video data set which we leverage for our training data set is those kind of videos where we are having object bounding boxes and referring expressions. So what we do here is that we take the frames, bounding boxes, and the referring expressions and input them to GPT-4o in order to produce a dense grounded caption. And for the masks, we generate them by feeding these frames and the corresponding bounding box coordinates to the segment anything model. So in this way, using existing data sources for 3 different type of existing annotations, we customize it to generate this grounded conversation generation data set. Okay, now we have the data, the right kind of a data to train this model. So this is the overall architecture of VideoGlam, and it has 3 key components. So one is the large language model. The second is a dual visual encoder, which emphasizes both spatial and temporal feature representation. And the third one is the pixel decoder to again project back to the visual space, the corresponding mask information. And this connection within these 3 different component is facilitated by tunable vision language and language vision adapters that kind of enable this alignment that we require, first moving from the feature representations to the LMM space and from LLM to back to the visual space. And then we also have the LLM, which is LoRa fine-tuned. So only thing that are trained here or fine-tuned here are the two projection adapters and the fine-tuning of the LLM. The rest is kept frozen. Okay, so here are some of the some other results about VideoGlam on grounded conversation generation task. And as a reminder, this task aims to provide video level detailed captions with specific phrases which are directly tied to the corresponding segmentation masks in the video. So given a user query, the VideoGlam generates textual responses and then grounds them using pixel level mask. So to obtain this kind of an output, we sample the prompt, something like provide a detailed description of the video and respond with interleaved segmentation mask for the corresponding parts of your answer. And in this way, then the model generates a detailed caption with interleaved segmentation masks. So here's another example. So in addition to grounded conversation generation, it can also do referring expression segmentation, a standard task in video understanding. In the same way, we can customize this VideoGlam model for that task as well. Okay, now let's look into the second research problem of developing video LMMs that are designed for spatiotemporal point grounding in a sequence of frames. So in many cases or instances in real world scenarios, we not necessarily need a segmentation mask as an output, and we are more interested in getting, let's say, the counting of the objects in a video, or for instance, pointing in case of an embodied AI agent or in other scenarios, so that we can perform some action task on top of it. So the VideoGlam architecture, which I showed before, can generate dense spatiotemporally coherent masks. However, that architecture or existing models does not support free-form text condition pointing with respect to the textual descriptions in videos. So the research question here is how we can adapt video LMMs for fine-grained spatiotemporal pointing that is conditioned on textual descriptions. And as I said, this enables many different applications, for instance, agents, robots, or web agents that can act by pointing in their environment. So for instance, in case of navigation to pick an object, or to user interface in case of digital agents for customization. And as a byproduct, one can also do counting by pointing. So for instance, chain of thought pointing can serve for counting tasks as well. And this has many different applications, for example, traffic monitoring or surveillance, where assessing object quantities provide informed decision in critical situations. And there exists a work on pointing in images. So Molmo is an architecture from LNAI Institute. It will be presented at CEPR in the main conference. It can do pointing in images. However, it is specialized for image scenarios, so it struggles to model the temporal dynamics inherent in video data, which we aim to investigate specifically. So this is an example of video Molmo architecture, which we have introduced recently, that is tailored for fine-grained spatiotemporal pointing conditioned on textual description. So for example, here is an example. So given here a complex referring expression in natural language to identify the white pigeon that has moved slightly from left to right among 5 pigeons, which are all in close proximity in this video sequence. So we can see existing methods. For instance, the video glam method, which I just presented, or video Lisa method. Also, if we want to customize the static image Molmo for videos by plugging it in the SAM2 architecture, they all struggle in different cases. So for instance, they can either, they are either stuck into different object, or they kind of lose track of the different objects. So here we can see in the yellow pointer, the pointed pigeon in our case, despite in this complex query, it can able to really point the object, the desired object, denoted by a star, followed by a segmentation mask in red for these complex query. Okay, so this is an architecture. So as I said, we would like to have the temporal modeling here. So the main novelty here is a temporal module to get into this temporal information. So we have, in total, we have visual encoder, we have a temporal module, an LLM, and also because most of the data sets are customized for segmentation outputs. So we also have a post-processing step where we are leveraging SAM2 capabilities in case if we also would like to convert the predicted points into segmentation masks as well. So as I said, the main novelty here is the temporal consistency. So for that, we introduce a temporal module, which employs a multi-head cross attention operation, where the query comes from the current frame and the key and value comes from the mean of the previous frames. So that kind of ensures that the current frame attends to the information from previous frames as well. And the output is fused with the original features to enrich these temporal cues while preserving the spatial details of the current frame as well. So we can see that the input is both the mean of the previous L frames and also the current frame as well. And then these resulting frames are passed to the LMM along with the textual query to process this information and to obtain the output points corresponding to the objects. And as I mentioned, that many of these data sets are designed to evaluate the segmentation mask as an output. So we also have a post-processing module that takes the prediction from this video Molmo and leverages the SAM2 and temporal fusion module to propagate the points across all the video frames bidirectionally. Okay, now in order to train this kind of a model, like VideoGlam, we also need a specialized training data set. Since there is no existing spatio-temporal pointing video data set to train such a model. So what we did is, again, we leverage existing data sources to customize it for this kind of a task. So, and at the end, we got around 72,000 video captions with around 100K object pairs. It is, again, a point level supervision kind of an architecture. So what we did is that we construct this point level supervision from frame level masks using a semi-automatic process. It's a very simple way, is that for each corresponding frame in our video, we sample K points on the mask and then pass those K points to the SAM2 in order to generate this candidate masks. So then we can have K candidate segmentation mask. Then the point with the highest intersection over union candidate mask with respect to the original mask is selected as the optimal annotation for corresponding to that point in the video. And for the existing video benchmark data sets. The sources come from, for instance, refer Davis or refer YouTube was or Lazot, and also reason was. So these are the data sets which we use and combine them and customize them for video Malmo training. Okay, so here are some of the results. Again, to show the generalization capabilities of video Malmo, we also designed a specific benchmark. We call it video pointing and segmentation benchmark, or VPOS bench. It is curated. The test set comprised around 100 videos and 1K manually annotated object points. And for mask-based evaluations, we employ the SAM2 model to convert these point annotations into segmentation masks. And most importantly, these examples show kind of an out of distribution results. So for instance, in our training set, we do not have any such kind of videos that point towards this embodied agent architecture or surveillance scenario, or for instance, this traffic light or this cell tracking. So these are all the different kind of scenarios that we have, 5 different categories, as I said, the cell tracking, egocentric videos, autonomous driving scenarios, video GUIs, and robotics, which kind of really test the model's capabilities in case where the model has not been trained specifically for this kind of videos. So we can see, for instance, in the second row, first example, on the left side, the model is able to correctly point to the traffic light in this challenging scenario, despite never encountering such a scenario during training as well. Here are some quantitative results on the right side. Again, we evaluate the model on 4 challenging tasks. So for instance, point grounding, counting, referring segmentation as well. For point grounding task, we customized or introduced a new data set called VPOS bench. Some examples are shown on the left side for this benchmark. For the counting task, we utilize the kinetics dataset where object counts are ranged from 2 to 13. And for referring video segmentation, we use the commonly used datasets like Mavis and Ref Davis and Ref YouTube datasets. For point grounding, we follow the original Malmo paper for images, where we present the results in precision recall and F1 score. And for mask-based evaluation, we use the standard metrics used for video object segmentation, like region Jacquard, boundary F measure, and the combination of both region Jacquard and F measure. And for the counting task, again, we compute the error as a metric to evaluate the results, for instance, in case of mean absolute error and exact matching accuracy. And we can see from the results that the model kind of performs favorably compared to existing architectures. A more, I would say, interesting comparison and a fair one is with Malmo plus SAM2. So this is the static image architecture that is customized, or in this case, by leveraging the SAM2 case, we are using exactly the same LLM, same settings. It's just that our architecture is customized to handle these videos, and that kind of reflects in these different tasks as well, how the performance is kind of improved compared to just adapting the static image Malmo with SAM2. Okay, so I will move on to the second part of my talk. So the results I showed were more on the grounding scenario, or how we can get more semantic understanding of the video content by customizing this video large multimodal models. I will now shift my focus on culturally aware multilingual video LMMs. And the main motivation again stems from the fact that if you have worked with video LMMs, whether they are open source or API based models, one thing that is common is that they really excel in English language. Of course, they support some multilingual capabilities as well, but most of these capabilities are for high represented languages, if I use the term in natural language processing. So low resource languages, or languages where we do not have a lot of data, those languages are still struggling in case if we really want to use it. So for instance, if we want these models to be used for, let's say, for mathematical reasoning or any educational task in any African country, ideally we would like to have these cross-lingual and cross-cultural capabilities in these video LMMs to really make their use more inclusive and effective in real-world scenarios. So we observe, again, our observation stems from the fact that existing video LMMs struggle with cultural and linguistic inclusivity. And specifically, I point out to two specific languages like Sinhala and Tamil. So Sinhala is for the Sri Lankan people, and for Tamil is a specific regional language spoken in southern India. So these models really struggle, we observe, in such kind of a scenario. And if I look into this landscape of existing video LMM benchmarks, we can see that, yes, there are multiple benchmarks that test standard reasoning capabilities in videos, or they test mathematics capabilities, or some other kind of a scenario. However, all of them are kind of mostly either English centric, or even if they cover multilingual representations, they are only centric to high resource languages, very few languages, and most notably, they do not cover the cultural part or the cultural sensitivities associated with that. So here in this table, the human questions were created. So in case if the type is human for annotation type, it means questions were created in the local language. If it is human plus auto, it means questions were created or generated using GPT-4o and later validated by human experts. And in case of auto, the questions were generated or translated automatically without any human verification. And to testify this, for instance, so here are some specific failure cases in case of GPT-4o with different language scripts. So for instance, in this Sinhala language, which I'm showing here, the question was about the event celebrated in the video, and the model correctly identifies the cultural significance. However, it fails to respond grammatically correct in Sinhala language. So this is a language proficiency error that we can identify in this case. However, the error could also be if the model is not able to identify correctly the cultural sensitivities or the inclusivity as well. So by given this motivation, we have introduced recently a new video LLM benchmark that is more culturally inclusive. It covers 14 different languages, including several underrepresented ones. So for instance, Sinhala, Urdu, and Tamil. And the English languages, the other languages are Chinese, Spanish, French, German, Hindi, Arabic, Russian, Bengali as well, and Japanese as well. So it really covers around 2/3 of world population. And importantly, we also have cultural context here. So we have 15 total categories. 7 of them are general categories, which we borrowed from existing video LMM benchmarks, and 8 categories are exclusive categories, which we have in our benchmark, and they correspond to the cultural part of it. And importantly, all the benchmark is natively verified from language experts in the corresponding language. So this is how we kind of ensured that the benchmark actually covers the real authentic essence of the culture of the corresponding country. So this is just a discrete distribution with respect to different languages in our benchmark. As I said, it has 14 different languages, and this is the 8 cultural categories that we have in our benchmark that kind of covers different aspects such as lifestyle, to festivals, to rituals and foods, or to local landmarks as well. And we can see that the proportion of the distribution in the benchmark is quite uniform with respect to these 8 cultural representations. So here is the data collection and verification pipeline. In total, we have 8,000 diverse sampled, which are manually verified from native experts for the corresponding languages. And we include both open-ended and multiple choice questions. So we have both. And even in open-ended questions, we have short questions, we have long questions as well. And the benchmark also offers diversity in terms of the video length. So for instance, we have short videos, we have long, medium length videos, and we also have long videos as well. And the cultural part is curated from the on the left side. It is mentioned. So for instance, we scrap cultural videos from scratch using country language and subtopic triplet, and then pass it to GPT to get the representation. And then with the help of manual of native speakers, we then curate this question answer pairs for each language from scratch. And for the English language, we then do the translation back from all the 13 languages into English. And for the generic part, which is on the right side of this figure, we leverage existing data sets and we just do the translation using GPT-4o, and then we again have a manual native speaker verification step just to ensure the quality of the generated samples. And in addition to the benchmark, we also proposed a model. So we again assemble existing video benchmarks. We do this translation automatically into 1.2 million samples using GPT-4o, and using this instruction tuning data set. Then we just fine tune existing video LMM. In this case, it was Lava 1 Vision. So there is nothing change in terms of the architecture. Here, the only novelty part is this dedicated 1.2 million instruction set that is on 14 different languages, which we leverage in order to fine tune or instruction tune this model or adapt this model. So it has an inbuilt LLM. It has two-layer MLP projections, and then we do this concatenation with the text embeddings and pass it to the language model to generate the responses in any of these 14 languages. So here's the performance comparison. So Vimal is actually our model. On the left side, we are showing the performance comparison with respect to open and closed source models. And we are also decomposing the performance comparison with respect to high resource languages and low resource languages. So low resource languages in this case is Sinhala, Tamil, and Urdu, whereas the other remaining 11 languages are considered as high resource languages. So there are several conclusions that we can infer. One is that there is a substantial amount of gap between open and closed source models, and this gap tends to increase if we go in the low resource languages. So low resource languages are really, the open source models are struggling in case of low resource languages. Our pre-trained model, which is using a dedicated 1.2 million instruction set, kind of bridges this gap. So we can see the performance improving specifically in case of low resource languages represented in the yellow part of this plot compared to, let's say, Lava 1 Vision, which is kind of our baseline model. And then on the right side, it's a comparison on general and cultural domains. So for instance, the ones in blue are the cultural categories, and the black one are the generic categories in this case. And we can see again that the performance of GPT is quite well on most of these categories, and how the cultural representation is somewhat compromised in this open source models as well. So the conclusion is that there is still some way to go if we really would like to have these models or video LMMs more culturally inclusive. Okay, so now I will move to the last part of my presentation. So how we can make these video LMMs more efficient so that we can actually use them on device, on resource constrained components. So there are notable strategies in literature. So you can do knowledge distillation. One can also use some hardware accelerators or whatever specialized hardware you would like to do. However, if you want to work on this core problem of how we can actually make the whole architecture or the whole video LMM more efficient so that we can have it on device on any resource constrained devices. This is something that is still an ongoing task. So in our recent work, which we named as Mobile Video GPT, we explore developing efficient multimodal frameworks. And the idea was if we can design an accurate model with fewer than billion parameters. So in this case, we introduced two model designs. One is 0.6 billion and the other one is 1.6 billion model. And we compared the performance with some recently introduced models of similar category on 6 benchmarks. So these are the standard benchmarks which are used for video LMM evaluation. And notably, our performance is quite comparable considering its size, and most importantly, the throughput, which is computed here in frames in tokens per second. This is quite high. So it kind of offers real-time capabilities that have been tested on a single A6000 GPU. So the model size in this case is less than 1 GB model size. It has only 3 GB of VRAM, and its inference speed is around 46 tokens per second on a single NVIDIA A6000 GPU. So this is just an example of a practical example where the model is asked to describe the video in detail. The model successfully generates a rich video description. So it's not just recognizing objects or actions, but it is also capturing interesting details. For instance, it actually captures the clothing or the body language and the room setting as well. So for instance, it says it's a cozy room with wooden flooring, so it kind of highlights more detailed semantics, and it's quite impressive in because of the size of the model, I would say. Okay, so here is the overall architecture of the model. So the video frames are passed to an efficient image encoder to extract the spatial frames. And then these frame features are then passed to the attention-based frame scoring mechanism, which identifies which frames to select and which frames are redundant. So in this way, we are reducing the processing as well. And then next we have an efficient video encoder that processes these selected frames to capture the temporal feature. So the resulting spatial and temporal representations are then projected into a unified visual language space by the help of this efficient token projector, which are later combined and pass it to a small language model to generate this comprehensive responses. So the novelty or the focus here is on two things. First is this attention-based frame scoring, and the second one is this ET projection layers, how it can really um, make it more efficient. So in case of attention scoring, frame scoring, it's basically just selecting frames. So for instance, if we have 16 frames, we typically select half of them based on this attention-based scoring mechanism. And then this is further reduced in case of ET projection layer. Okay, so this is the training strategy. We have this training done in multiple patches. So the stage one focuses on pre-training the image token projector with this efficient image encoder using this ET projection to map this image feature. In stage two, then we extend it to videos by pre-training the video token projector with the help of this efficient video encoder. And then the stage three actually introduces this instruction tuning where we both the image and the video encoders tokens projectors are kind of are learnable together with LoRa fine tuning of this small language model. And as I said, our main novelty is this ET projection layer. So this is the architecture of this lightweight design in contrast to the MLP layers, which is typically used in this video LMM. So it comprises a feed-forward network to refine the token embeddings for desired representation capacity. And then it has this token reduction step where it leverages this global average pooling and followed by a positional encoding module with skip connection in order to retain the spatial and as well as the temporal information. So here is an example comparison on a video of a nighttime field hockey game. So the baseline model is the first one. Here it kind of generates incomplete or generic description, and most importantly, it misses important details such as the final hockey score in this game. In contrast, the mobile video GPT, which is the last results we have shown here, it's quite fast, its latency is really good, and it also generates, in this case, the accurate results as well. So in this case, it kind of predicts the correct score of this hockey game in this nighttime case. So as I said, the main difference here is that the Lava 1 Vision, which is popularly used, uses a simple MLP-based projector that handles 32 frames, input frames, which means each produce 196 tokens. So in total, it has around more than 6,000 tokens. By contrast, our efficient token projector layer combines with the frame selection mechanism really reduces this token processing. So that makes the latency really good. So for images, we consider only 16 frames, each represented by around 144 tokens, which yields around 2000 tokens in total. And then for videos, we select 8 of those frames based on this attention scoring mechanism, where each produces around 49 tokens. So this results into around 400 tokens. And if I do the comparison, then compared to Lava 1 Vision, which is leveraging around 6,000 tokens, we're only using around 2,500 visual tokens. So that really helps this efficiency part. Okay, just to conclude, today I discussed 3 different research lines with respect to advancing large multimodal models for videos. The first one is specifically tailored for detailed video understanding content in terms of enriched semantics. In this case, we can look into developing video LMMs with spatiotemporal pixel grounding capabilities, or in case if that is if pointing is something that is desired, we also showed a dedicated approach that can do spatiotemporal point grounding in videos as well. Then the second part, which I touched base, is how we can look into culturally aware multilingual video LMMs so that we can make languages and cultures more inclusive in terms of our video LMM construction part. And then lastly, a very important research line is how we can make these video LMMs more efficient without compromising their accuracy as well. And for all the methods which I have presented here, both the dataset part for model training as well as the model weights are publicly available in case if you would like to use it. So with that, I will conclude the talk. Thank you very much.
Any questions? Any questions? Or
for the culturally aware multi-input video, I wonder how you sourced the videos to be culturally relevant to the homepage.
Okay, so yes, so we actually source the videos. We scrap the videos from internet and different channels in the original language. So we ask the native speakers for a particular language. Let's say in case of Tamil, we ask a Tamil native speaker. So we have the categories that we have identified. So for each corresponding category, we sample a lot of videos from internet in the original language, and then we further have a selection criterion where we only take 3 to 4 videos which kind of require cultural understanding in order to get the correct answer, and also is appropriate for that cultural concept as well.
Thank you for the presentation. I wanted to ask about the criteria for making sure that the videos and the text for the cultural aware are appropriate for the given question answer. So what was the criteria that you guys decided upon?
Okay, so as I mentioned in the previous question as well, so we look into different aspects. So the first one is that for the cultural part, we started curating the video samples in the original language. So that was the first thing. And then we already have identified, let's say, these 8 cultural categories. And for each cultural category, we ask the native speaker for that particular language to look into the video sources in the original language to select a set of videos. Then we have filtering mechanism in order to identify whether the cultural aspect is accurately reflected in the video, and most importantly, that the video source is required, or the visual information is required to correctly answer that cultural category or that cultural question as well. So the cultural questions, again, then in our data set, we have both cultural questions as MCQs and open-ended questions as well.
My question was regarding the filtering process. Was that manual or was
it was manual? So everything we did with the cultural part is manual and with the help of native speakers, because that is the only way to ensure that we have less bias and more accuracy, accurate reflection with respect to the cultural content.
Thank you, Will. I have one. For the video collaboration, how do you guys select the samples for them? So, for example, did you have samples where there might be 2 objects for which the pointing might jump between those kind of objects, and how would you evaluate?
So this is actually a very good question. We have such kind of samples, and in the examples I showed, we also make sure that we have out of distribution scenarios as well, which are something that were not seen during the training part as well. The model, I would say, okay, if it is asked to point to, I mean, there are still certain limitations of this kind of a model. So if it is asked to point to 2 objects and kind of they've changed the identity, all those kinds of things, then the model kind of struggles. We have also put it as a limitation because we have observed that in the model in the paper as well. And I think for the counting part as well, because we are using kinetics, a data set for evaluation. So for instance, it is 2 to 13 objects. So if in case if you really want to go in a densely packed setting, then that is another problem altogether as well. So I think, in my opinion, my answer would be that this is the first approach in this line. I think there is still a lot to do in order to improve their performances. So if you would like to use a dedicated counting approach, it might work better than this kind of a video LMM kind of an approach. And this is a gap which I hope the community is going to bridge with the follow-up works.
You mentioned 3D. So do you have evaluation for some person?
No, we don't have
works
that.
out?
No, we don't have that. We don't explicitly do that kind of a thing. Sure.
Is there any work experimented on fine-grained video and fine
For which work? For mobile, yes, we have actually one data set which kind of captures or kind of evaluates fine-grained actions at atomic levels as well. And I think in some of those we are performing quite well, but in some which requires much more fine-grained understanding, this is something that the model still kind of struggles sometimes. I think we have this category. I don't remember now the exact number of categories, but we have this table in the paper as well.
Just a small announcement, everyone. So because we are running a bit late, we'll start the panel at 1:15 instead of 1. Yeah.
So I will put my charge. Yes. Sure.
Yeah,
Go ahead.
you have a attention-based frame selection strategy, and which is also a frame level. And Germany also uses redundancy, let's say, user frames, background, and some other things maybe and change them. So how do you do with this kind of redundancy?
We don't.
This is also
Yeah, this is actually a good question. We don't do it explicitly. I think this is something that can be taken care of. We just rely implicitly that with this kind of a frame selection category selection strategy can also look into this kind of redundant frames as well. So as I said, instead of 16, we reduce it to half. We use 8 frames, and we saw the performance to be reasonably okay with that kind of a thing. But again, if you would like to do a much more refined frame selection category, there are methods, not maybe in video LMMs, but let's say frame selection in video understanding domain that could be applied to further improve this frame selection category, to even reduce the number or maybe select some more dynamic frames which probably can improve the performance as well.